an elephant and a feather falling, which experiences the greater air resistance? The elephant or the feather? And remember, air resistance is dependent upon only two things. One of them is speed, and the other is speed and, excellent, surface area. Those are the two factors that impact air resistance. So why is it that the elephant has greater air resistance? Well, it's falling faster, it's got greater speed, and it's clearly got greater surface area too. But if it has a greater air resistance, why is it falling faster? Let's look at it in terms of the net forces acting on these two objects. First, the elephant. The elephant has its weight, and the weight is great. We're going to use a big WT to indicate its weight. And the weight is always downward. It's the force of gravity. Now, its air resistance is also pretty darn big. I'm going to use a R for air resistance. But we see here that the weight is nonetheless greater than the air resistance. Let's look at it from the point of view of the feather. The feather has a small weight. And it can be the case that the air resistance is equal to the weight. Notice here that the letter R I did for the feather is smaller than the letter R for the elephant, is to say the air resistance of the feather is smaller than the air resistance of the elephant. But check this out. The air resistance and the weight are the same. They can be exactly the same. Weight is always downward. Air resistance is always upward. And that's why I have the subtraction sign here. You can subtract to be zero. That's right, zero net force. What's that mean? It means the feather might be falling at 1 meter per second, then at 1 meter per second, then at 1 meter per second. Its speed is not changing. There's no net force. It's reached what we call terminal velocity. Eh? What about the elephant? If we wanted to get terminal velocity, what we're going to have to do is increase this letter R so that it's the same size as this WT. How can you increase the air resistance? Well, the elephant's going to go faster and faster and faster. And as it does, this air resistance gets bigger and bigger, and it too will eventually reach terminal velocity. But the speed of its terminal velocity is pretty big. You don't want to hit the ground with such high terminal velocity. But there's another way to change this air resistance. That's right, by surface area. How are we going to increase the surface area of the elephant? Excellent. How about a parachute? We put a huge parachute on the elephant, and that parachute increases the air resistance. So that gets to be a big R. Excellent. And the R subtracts from the weight, and you have zero net force. You have terminal velocity, and hopefully a terminal velocity that is slow enough for a soft landing. That's good science.